Hello everyone, this is Group 9 and for our final project we'll be talking about the Kaggle competition about Parley Sunny with a change of hashtags, and we'll be using different machine learning techniques. In this project we will conduct model training, prediction and model analysis for the Kaggle competition Parley Sunny with a challenge of hashtags. The challenge is to analyze the tweet and determine whether it has a positive or negative or neutral sentiment, whether the weather occurred in the past, present, or future, and what sort of weather the tweet referenced. We'll be illustrating our results in the following presentation. Now we will be implementing our super vector machine algorithm in our project. The dataset we will be using for this is the train and test dataset. For this project, there are three features available for us to use, but we'll be using only two, which are state and S1. We extract the required features and split into training and testing data. We have the 80% of the data that is used for training and the 20% which is the rest for testing. We can also make use of sklearn library, and we just call related functions to implement our SVM model. Now as we can see, we clipped the weights as the test data, then we extract the features from the test data and predict the values. We obtain the predictions and compare it with the actual values and print the accuracy of our model. Now we can see the accuracy level of our model. The support vector machine algorithm gave us an accuracy of 79.80%. Now we will implement the k-nearest neighbors, which is a supervised machine learning algorithm that can be used for either regression or classification tasks. In this case, we will be using it for classification task. Now we can see that we started evaluating the model, and we also started to make predictions on the data set. On the picture that you see, on the screenshot that you see, the k nearest neighbor algorithm is imported from the sklearn package. We also created a feature and target variables, split data into training and test data, generate a KNN model using neighbors value, train or feed the data into the model, and predict the future of it. In this example, we are creating a plot to see the k value for which we have a normal accuracy. It looks like the classifier achieved a 79% accuracy on the test set for this KNN algorithm.
This model is on hyperparameter tuning and model evaluation. This is for the Partly Sunny with a Chance of Hashtags Kaggle competition. As you see here, we're importing pandas and NumPy in order to read the data set. And the data set consists of tweets, locations, and confidence scores. In this slide, we're using sklearn preprocessing to import label encoder. And this provides a very efficient tool for encoding the levels of categorical features into numeric values. Label encoder encodes labels with a value between 0 and n classes. Underneath that, we're using transform on the training data so that we can scale the training data and learn the scaling parameters of that data. Here, the model that's used will learn the mean and variance of the features of the training set. These learn parameters are then used to scale our test data. At the very bottom, we're importing train, test, and split. And this is a function in sklearn model selection for splitting data arrays for training data and for testing data. With this function, we don't need to divide the data set manually. By default, this function will work for these for two subsets. Pipelines are used to chain multiple estimators into one and automate the machine learning process. This is extremely useful as there are often a fixed sequence of steps in processing the data. The sklearn preprocessing standard scaler is a feature and then scaling to unit variance. Unit variance means dividing all the values by the standard scaler makes the mean of the distribution approximately 0. The sklearn decomposition importing PCA, the principal component analysis, the singular value decomposition of the data to project it to a lower dimensional space. The input data is centered but not scaled for each feature before applying the SVD. And of course, there's importing a linear model and logistic regression as well. This slide uses K-fold cross-validation to assess the model performance. K-fold cross-validator provides train test indices to split data in train test sets. Split data set into a number of consecutive folds without shuffling by default. Each fold is then used once as a validation, while the remaining folds form the training set. This is the tuning the hyperparameters via grid search portion of the code. So hyperparameter tuning is choosing a set of optimal hyperparameters for a learning algorithm. A hyperparameter is a model argument whose value is set before the learning process begins. The key to machine learning algorithms is, of course, hyperparameter tuning. And so we are importing grid search CV, and it's a library function that is a member of sklearn's model selection package. So in the end, we can select the best parameters from the list.
We started this process by loading the information from a CSV file using pandas. Next, we found the unique elements in the models, counted these elements, and transformed our data from the train and test files to match. Then separated these values into arrays from for the use of elements in the program. This can be shown on the top picture for the top step and the bottom picture for the bottom step, as noted on their bullets. We set up the TensorFlow Keras and compiled it as shown on the left picture. Then we set our train information into the Keras model and plotted into charts shown on the right side in the picture. We calculated the values of empathy and accuracy on the steps of the slides before. Displayed them into easy to read charts as shown below. The with drop data is before we drop the data that is unneeded on the columns, and without drop data is after we dropped the data that is not needed. These graphs bring some interesting elements to the life because dropping the data barely changes the data, but does result in a less of a value loss. Accuracy stays about the same, but the data present with the data is not dropped. This is interesting because our original hypothesis was the data drop would improve accuracy, which it did, but only by a value of 0.0171, which is very slim. Finally, we checked the distribution of elements and placed them into a nice graph, which resulted in a normal distribution. The code to do this is shown on the left, and the graph is shown on the right.